Hey everyone, I'm back for another lecture. Try to make this one a little shorter than the last one. I apologize, that last one I went way too long on. So I'll try to make this one a little bit better. But I will say this. When we're talking about getting into modern environmental type issues, these last few chapters that we're going to go over are going to be kind of the meat of what we're going to talk about with regards to current events. What's being talked about in the news, what the politicians argue about all the time. And you hear a lot of this person says this thing, one person on one side says the other thing. This is going to help you to see the reality of some of these issues that are talked about so much in our news cycles and politics today. And hopefully give you a better understanding of the truth about what's really going on and how our resources have been used, the benefits of those resources, even the ones that are kind of bad for us today that we see. There's always a good part and a bad part to most situations. So while some traditional type fossil fuels have been good to us in the past, they serve their purpose. Going forward, that might not be the best option. And we're going to touch on a lot of those different things as we go through this chapter. So again, this is chapter 13 on conventional fossil fuel resources. And I'll go back to something I mentioned before. If you look in your textbook, the textbook is divided up in different sections. And I kind of reorganized a couple of these sections. And I included the fossil fuel resources with the section on the earth resources. And then I put the renewable resources, which is also an earth resource, but I put it in the next section, the last module that we're going to study, because it's getting more into what humans can do going forward to help the environment, to remediate problems that we may have caused in the past. So I decided to include those resources in the next module. So if you're confused on to why the book modules are a little bit different than mine, again, it had to do with timing during the semester, how it was organized, and I thought it was a natural break as well in talking about the two different types of fuel resources. So to understand the fuel resources that we have on the earth that are natural, we first have to understand, how do humans use energy? Why do we need energy? What is energy? So when we talk about energy, as far as what humans use, there's different types of energy that we see, that we utilize in our environment. Of course, y'all are probably familiar with most of these. Electrical, chemical energy from chemical reactions, thermal, which is basically heat energy, kinetic is energy that's associated with motion of things. If you understand any type of generation of electricity, typically that's done where some type of energy is used primarily to make some type of wheel spin. That would be kinetic, and that's what makes electricity. So you're actually going through three different types of energy to get to the ultimate end goal of producing electricity. And then we have potential energy. I'm not going to talk about that one a lot. Nuclear energy and radiant energy. Now, I am going to touch on nuclear energy in just a little while as far as an energy resource that we have available to us. So this is a really good diagram, and you have to look at it as kind of a whole concept of what is utilized. And the reason it's really good, it kind of goes through some of the different types of energy that we're studying, but also shows you how much or how many different types of energy are utilized just in the processing of food that we consume as humans. It starts with the sun, that's nuclear radiant. It goes to photosynthesis, which is radiant and then chemical within the plant. The chlorophyll in the plant produces photosynthesis, and that is the chemical part of that. You harvest that crop, you use electricity and thermal heat to cook the food, and then that food is processed within our bodies, and that's actually energy for us within our bodies. Most of you probably know. If you don't know, you should know. When we talk about the calories that we eat in our food, we talk about that, about losing weight all the time. That's actually a measure of energy. A calorie is a measure of energy. So this is a really good diagram, and again, you'll see this more on your test most likely. So this is just a really good example of how we use the different types of energy in different processes. So energy conversions. So the first law of thermodynamics states that energy cannot really be created or destroyed. It can only be changed in the way it moves or the way it works. So you can change forms of energy, but you can't create or destroy energy. So that means the energy is already out there, and we're just harnessing that energy from some source, and we're changing that energy to a form that we can use. So that's the simplest explanation of that first law of thermodynamics. In this photos, you're seeing some kind of throwback technologies. Before the Industrial Revolution back in the 1800s, humans realized that they could harness energy from renewable resources. You see some old water mills there on the left. That's using kind of a primitive hydroelectric system that actually turns a wheel. Locally, most of you are probably from Kentucky, we called those grist mills locally in the old days, where they would actually take grain and they would grind it up using these type of wheels that turned to stone inside the building. And then you have the windmills that were harnessing energy back in Europe, back couple hundred years ago, 300 or 400 years ago. They used windmills for the same type of purpose. These windmills would spin. These were commonly found in all the Scandinavian countries, Denmark, Belgium, the Netherlands. That area was famous for their windmill technology back in the day. So here's where I've already mentioned that first law of thermodynamics. And this chart, I really like it because this just gives you an indication of why some of the changes that we're making in today's world we are truly making because of the inefficiency of some types of energy transfer. For instance, probably one of the biggest inventions of the history of humanity was the incandescent light bulb back in the 1800s. I think it was 1850s or 60s maybe, somewhere around that time frame. That was a big invention because all of a sudden we had light at night. We didn't have to burn candles to have light or some type of lantern to have light. So if we had electricity and an incandescent bulb, we could have light. And those incandescent light bulbs were used up until most of my lifetime, up until the last 15 years or so. We primarily used incandescent light bulbs. But if you look over to the right, this is the energy efficiency. So that is the amount of energy that you actually get out of this after you've converted it from one type of energy to another. So you can see how terribly inefficient incandescent light bulbs were. To get that light, we're wasting 95% of the energy that we're putting into that process. Terribly inefficient. So that's why a few years ago the government decided that we're going to phase out that type of light bulb. And of course a lot of people screamed and yelled about that because LED bulbs are more expensive and it's a change, and nobody ever likes change. Nobody ever wants anything to change because that's just the natural resistance that humans have to their lives. They like for things to stay the same. But if you look at the efficiency of an LED light bulb right here, you see it's 80%. So you're not wasting near as much energy consumption in this type of light bulb as you do in an incandescent. In addition to that, the LED bulbs last a lot longer. Yes, they're more expensive up front, but they're going to last a lot longer, whereas an incandescent bulb you're buying more often. So you can look at this list yourself. I don't have to go through all of this, but you can see the different efficiencies of different types of energy transfers, and in the middle column is the conversion. For instance, that light bulb, you're going to electrical to radiant. Radiant means waves going out from it, so that's that visible light spectrum. So you're using electricity to go to a radiant light. Same with an LED bulb. We talk about engines, you're going chemical, which is the combustion of a fossil fuel, to kinetic, which means you're turning those wheels in that engine to create power. So you can see that gasoline and diesel engines are pretty inefficient with regards to the use of that energy, whereas an electric engine is much more efficient, and that's one of the transitions that we're seeing today in our lives, going from gasoline cars to electric vehicles. And we'll talk about more a little bit as well. So when we talk about the different types of energy that's available naturally, we have renewable and non-renewable. So these are some examples right here in our line of thinking with regards to the energy that we produce. Our renewable energy would be solar. The sun shines all the time. It's a big nuclear reactor in the sky that we have all the time. And if it ceases to shine, then we don't have to worry about energy anymore because we will no longer be here. So that is a constant source of energy. Non-renewable would be fossil fuels. Now, fossil fuels they were made by natural processes, and they continue to be made at this time in those environments where they develop. However, they develop at such a slow rate that if we use all of them up now, it'll be millions of years before those stores are replenished. So it's not going to benefit us in the least, even though they continue to be made today. It's such a slow process, it's essentially nothing to us in our short lifetimes and on the geologic scale. And then the secondary type of energy that we use would be the electricity. So we're using those primary sources, which would be solar or nuclear or fossil fuels, to produce the secondary, which would be electricity, is what we actually would use in our homes. So here is a diagram of historical energy use in the United States. You can look at this yourself. One thing I do want to point out, I had to look at this for a few minutes because it's kind of misleading because of these lines right here. So the bottom red line is actually wind, solar, and geothermal. So you can see they have a long line drawn, but it looks like it's part of the graph almost. So it's kind of hard to tell that wind, solar, and geothermal are kind of out there by themselves. I don't expect you to remember the specifics of this, but just generally trends. So you can see the oil is the orange line, and it rose sharply through the 1950s, 60s, up until 1970, and then we start having these bumps, these up and down waves in this. That has a lot to do with human activity, our energy use, and politics, and especially world politics, as far as who has the oil. What are they dealing with that oil? What kind of crisis is happening at any given time? And we're in the middle of one of those right now. This textbook was written, it looks like from the things I've read in here, about 2018. So there's nothing about COVID in here. There's nothing about the Russian invasion of Ukraine. Both of those things will show up on this graph on out here. We'll see another sharp decline because of COVID and the Russian issue that's going on right now. The blue line is natural gas, and you can see it's rising steeply right now, and it continues to rise. Coal is the black line. It continues to fall. And then the red line I mentioned earlier, that is the renewables, and as you can see, hardly used at all until 2000. It slowly starts to increase, but the last probably 5, 6, 7 years, you see a sharper incline in this. It's not nearly enough, but we're starting to utilize these more and more as we go forward. Here is a simple diagram of how coal is formed. Coal is formed from organic matter, typically in a delta or swampy kind of situation near a coastline in most cases. Those seams of vegetation that fall into those damp areas, like think about a swamp. That's the best way as far as a visual image. You have a swamp, and this vegetation is falling into the swamp as it dies, and there's a lack of oxygen in there, so you don't have rapid decomposition. It's anaerobic, which means it's very slow. So the more and more of this that builds up over time, it compacts itself, it gets buried eventually by sediment, gets pushed down further, undergoes sometimes heat, but more likely just pressure, and it forms seams of coal. So that is how coal is formed in a very, very quick explanation. And of course, we have a lot of coal here in Kentucky. We always talk about the coal mines of eastern Kentucky. So this is a very good chart as well. These are the different types of coal here. You have peat is going to be, remember we talked about peat back, I think, was that in soils, is where we discussed peat before, where that's actually in layers right now. It hasn't been buried to the point that it's starting to form coal yet, but it's a very dark layer of very dense material. So when it gets deep enough, it starts to form lignite. And then as you progress, this is increasing pressure, heat, and time. So as it gets pushed deeper and there's more pressure, the grade of the coal actually increases. As we go forward to the right, subbituminous, bituminous, and anthracite, as you go to the right, these coals contain less volatile components, we call them VOCs in our industry, and more of the pure carbon. So this is more pure in nature, than the subbituminous would be. There's going to be more impurities in this. Therefore, this would burn a lot cleaner. You probably heard the comments on clean coal. All the politicians that want to stay with coal talk about clean coal. Well, that's pretty ridiculous, because the percentage of clean coal that we have, as you can see on this map, the clean coal is actually the green. And you can see how few of the deposits of coal in the United States are anthracite, which is the clean burning coal. Almost none. The low VOC bituminous coal is the next best as far as clean burning. These two are considered the two best to burn. And you can also see there are very few reserves of even that low volatile bituminous coal. Most of what we have here in Kentucky is going to be the medium and high volatile bituminous coal, and that is more of the dirty burning coal. It's not as bad as lignite or subbituminous coal, but nonetheless, it's not very good for the release of the compounds that cause global warming when they're combusted. You can see out west those blues and darker colors. Those are the really bad layers of coal. They pollute really bad when they're burned. They have a lot more VOCs in them when they're combusted, and those are not preferred, although they're a lot cheaper than the other types of coal. The environmental impacts of coal mining, we've kind of touched on this in the last chapter when we were talking about mineral resources as far as mining underground. You have subsidence. You see here, this picture looks a lot like the sinkhole pictures I showed you in our area for the caves, but this is actually in an area that has mines underground, and the ground is actually sunk in. We've talked about subsidence in like 3 chapters already, so you should be an expert on subsidence right now. Very dangerous for homes in the area or structures if you're mining under an urban area, for instance. Typically they don't do that, but it's still, if there are any structures here, that could be a problem. You have severe ecosystem destruction in eastern Kentucky right now, because they do have underground mines, but they also have strip mining and something called mountaintop removal that we're going to see in a couple of slides that is very, very destructive to the environment. Now, a result of burning some of these higher sulfur coals, the lower grade coals, was something called acid rain. That was very prevalent in my childhood. That was one of the big environmental things back when I was young. Through technology, they were required to put scrubbers on some of the stacks in the power plants where they burn coal, so they were able to kind of mitigate some of that through technology, and they also now burn the cleaner coals, so that is not as big of a problem as it was before, but it's still a problem. But you also still have the acid mine drainage that happens in these, even in these old abandoned mines. Even if they're not being used anymore, we've disturbed these to the point where water is getting into them, and there's drainage going through them and running out into the surface waters. So here's an example of some underground coal mining. some of the different ways that they do it. There will be a coal layer. Remember, this is a sedimentary layer, so you got limestone and sandstones above or below this, and they'll go in and mine a seam underground. Now, if they do a good mining system called room and pillar mining, they'll leave sections of stone unharmed, and that way it leaves some support for the layers above. If they go in and just take out the whole layer, of course this is going to fall in areas, and you're going to have significant subsidence in those areas. This is the example I was telling you about mountaintop removal. And I really wanted to hit on this for a couple reasons. This is a big issue in eastern Kentucky and West Virginia right now. It's terribly destructive to the environment. As you can see, they literally, it's what it says, they cut off the top of a mountain. They'll go through, and there might be a big coal seam right in this area. They'll just cut off everything above it, and they'll push it down the side of the mountain, get to these coal seams over here, take those out, and then they basically have an enormous amount of tailings and overburden that they just push down the mountain, and they fill up the stream valleys. So here you have where they just took off part of it, and they've partially filled in the valley, but here they took off most all of it to this flat level, and it's taken up a good part of the valley. Now they're still showing a little stream flowing down here. You're lucky if you have that. Usually they just put it flat and don't have anything. But even if they did this stream is going to be flowing through overburden and tailings. So what type of water quality do you have in that stream right there? It's going to be terribly polluted. On top of that, and that's another reason I wanted to mention that this year, because this past year we had these severe floods in eastern Kentucky. We had these untypical rainfall events there. Remember, we talked about the 1,000, 10,000, 100,000 year floods back early in the semester. We had those type of floods there in eastern Kentucky. What do you think happens to all that rainfall if their natural drainage is taken away and the valleys are filled in? There are numerous lawsuits right now from citizens that lost their families against coal companies for filling in these valleys due to that flooding. And it is a severe problem in Appalachia that not only are they destroying the ecosystems of these areas, but they're also completely filling in these valleys that you see here with sediment and destroying entire riparian areas that typically are used to drain the water out of these areas. Okay, now we're going to transition to petroleum, oil, and natural gas. So typically when we say petroleum, most of us think of oil. That includes natural gas as well, although we usually separate the two the way we talk about them. So oil is typically a liquid, and natural gas, of course, is gas. It's a gaseous, it's not a liquid at all. And you can see here the different chemical compositions. So you have hydrogen and you have carbon atoms. That's why you hear these called hydrocarbons, because all of the petroleum, oil, and natural gas are a string of hydrocarbons arranged in a certain way. And you can see here some of the different ones. This would be your regular gasoline. This would be diesel. You can see these are much longer and heavier types of molecules. But over here you have your gaseous molecules. These are liquid. Over here, motor oil is really thick. Over here you have your gaseous ones, your butane, propane, like you use in your grill out back, and you have methane. So these are the gases. These are the natural gases. This has become prevalent for us to produce our electricity in the recent years, because first of all, coal is not very environmentally friendly, and even though natural gas, when you burn it, it still produces climate changing materials that go into the atmosphere. It's much less than burning coal. So that's one advantage. The other advantage is, as technology has changed, natural gas has become a lot more prevalent in the market. So when you hear all of these politicians, especially in Kentucky, talking about how the hippies and the environmentalists are killing the coal industry, that's not what's killed the coal industry. What's killed the coal industry is natural gas. That's what's done it in the past several years. Now, of course, the environmentalists don't like coal either, and they're no fans of coal. So don't get me wrong, I'm not saying that they have nothing against coal. They do. But money drives everything. And the reason that the coal industry has declined so much has more to do with the economics of natural gas than it has to do with the environmental movement of the environmentalists. So I just wanted to point that out, and that they mentioned that in your textbook, but that's a real world thing that's been happening over the last several years. And this chart over here just kind of describes where and how these form. I'm going to let you look at those in your textbook and on this presentation. I'm going to kind of skip through some of this. This is just a geology of how oil actually, most of all how it forms, but how it accumulates under the ground. It'll have its parent material, but a lot of times it will migrate out of that. Remember how we have pore spaces in the bedrock, like we talked about with the water table back earlier in the semester? Well, that's where oil exists in a lot of these rock layers. And sometimes it'll find a less dense rock layer and it will flow to that less dense area along with groundwater and get trapped. And that's where we have our biggest petroleum deposits. And these are some of the different types that you see listed here as far as how they get trapped in these different type of rock layers. So again, for the sake of keeping this lecture a little bit shorter, I'm not going to go into this in great detail in here. Now, with regards to exploration and drilling, one thing that we've kept pace on the last few decades with regards to the use and utilization of oil is we've improved our ability to find it and get to it and take it out of the ground. So we go over in the textbook a few of the ways that we are now finding this oil using remote sensing, such as this cross section here of using waves put through the ground. It can be radar, sonar, not radar, sonar, I'm sorry, that you can put through the ground and you can detect anomalies under the ground in the bedrock layers. And that's how they can locate what they probably think is oil, and then they will drill down and test that to see if it is indeed oil. And then over here you have some different types of getting to this oil where we can now curve these drilling bits and get it to more places horizontally and not just vertically. So we don't have to put so many oil wells on top of the ground, but we can actually go down, and that's especially helpful when we get into our deep water type oil rigs. So here is a map of proven deep water oil reserves, and if you read through your textbook, you'll see oil reserves are typically formed. I talked about how coal was formed, and coal and oil are very similar with regards to their hydrocarbons. However, the oil reserves are more formed in a marine environment, where the coal reserves are more formed on a beach kind of delta environment close to the sea sometimes. Sometimes they're inland, but it's more of a terrestrial based plants, whereas oil was formed by marine based plants, seaweed, plankton, stuff like that settle to the bottom. So these are where all the major oil reserves are, proven reserves. In deep water situations, you don't see many in the Middle East right here. Those are not considered deep water. The ones in red are the deep water ones, kind of offshore out in really, really deep ocean water. And this is just a cross section of how a deep water well would work. So you can see here, this is the ocean. They get to the bottom and then they drill down and enter in these. I'm going to let you look at this in your textbook. Again, I'm not going to hit on this as much in the lecture. I'm going to let y'all look at this in the textbook. What I do want to talk about, though, is kind of the supply and demand side of oil and what we have to look like in the future, what we have to determine our fate is going to be. Because I'll tell you up front right now, this, again, I mentioned earlier, but this is a finite resource. So this is going to run out at some point on humanity. We're going to get to a point where we no longer have the viability to drill enough oil to supply the planet. So that's why there's a big push right now for renewables, more than there ever has been. You've got the climate change issue that's been going on, and it's been being pushed for a long time. But now we're getting to a point, and we're going to see in a few slides, there's been models done in the past that is pointing to this time period in human history right now is to where we're probably going to max out on our ability to produce oil in the next at least couple of decades. And then it's going to start declining. Now, we're currently in the middle of kind of a high gas price time. That has to do with politics, the Russian invasion, COVID, supply and demand, all kinds of stuff. You know, when you turn on the news, everybody's going to blame it on the political party in charge of the United States right now. That's really pretty irrelevant. I know that's convenient for a lot of people to talk about that, and there might be some relevance to it in some cases, but for right now, for instance, there's a myriad of things that's going on in the world that's affected oil prices. The Russian invasion of Ukraine was a big one. COVID, the rebound from COVID was a big one. And then you've got our dependence on foreign oil. So we've had this discussion since the 1970s. 1970, we had our first problem because that's the first time that the United States started importing oil. And as you can see on these graphs right here, we have our conventional gas wells. The production rate is going down, and it's going to keep going down. Now, as we go forward, we might slow it down with technology. Our scientists and our engineers might come up with ways to get more oil or go to places that we haven't been able to do it economically before, but eventually that's going to run out. We have what we call tight gas wells. These are gas wells that we've only been utilizing the last few decades because traditionally they were not economical to utilize. A tight gas well, a tight gas reserve refers to gas or petroleum that is housed in bedrock or its layer, and it's very dense rock. So it's very hard to get that oil to come out of that rock. And that's where you're going to hear about fracking. When we talk about fracking, most of you probably heard about that in the news. It's very controversial. It's a very destructive practice. It has a lot of environmental implications. But what it has done is it's allowed us to get at more petroleum reserves that we were not able to get to before. So that's what this red line is, the tight gas well. So another thing we have to think about is the type of oil that we're able to access. So for pretty much since we've been using oil, we've been using the good stuff, the easy to get to stuff, what we call light crude. That's the easiest to refine. It has the most beneficial chemicals in here that we want for our purposes, which is gasoline. And you can see here, basically when you refine oil, it's just like distilling water. Remember water desalination where they boil the water evaporates, they recollect it, the salts evaporate out. That's basically what we're doing here. It's more of a chemical reaction, but they're basically heating up this oil, and as it grades up in this cylinder, and this is a very simple explanation, but the different atomic structures, the different materials will tease out at different levels. So you get different products. And this is why when gas prices go up, everything else goes up as well. Not only does it go up because we have to have gas to transport all this material, but as you can see on this list and you see in our textbook, there's a lot of other chemicals that come from this refining process that are used in everyday materials, from plastic to fertilizer, different types of fuel, kerosene, all kinds of different products come from the distillation of oil. So that's why so many things go up so much when gas prices increase. And again, I mentioned the heavy crude and light crude. Light crude is beneficial for us as far as refining. We're starting to have to use heavy crude more and more because there's less and less of the light crude, and that's driving up prices as well because if we have to use the heavier stuff, it costs more money to refine it. So that's part of the price increase as well. So you're seeing as we're making this discussion through this chapter, there's a lot of complex reasons why gas prices are what they are. It's not just some politician decided they're going to make some decision and it's all going to change everything. It's not that simple, and that's not what it's about. So again, the environmental impacts of petroleum, I think most of us are well versed in this. The combustion of these fossil fuels puts gases in the air that contributes to climate change, to global warming. We have tremendously increased the amounts of these gases in our atmosphere. They're called greenhouse gases, and what they do is they trap more heat inside the Earth's atmosphere, raising temperatures on the Earth's surface. And there's a lot of people out there that want to say, oh, this is a hoax, it's not real, humans can't possibly have that much of an effect on the environment. Remember what I told you over and over again in this chapter, that the Earth is always working toward that baseline, that equilibrium, if you will. And basically what we're doing by taking this material, this oil or coal or whatever it is, we're taking it out of the ground. Now, for millions and millions of years, this Earth has evolved with that material inside the ground. So the Earth has stabilized. And now we are going in and physically redistributing all of that stuff, all of the coal, all of the oil, all of those chemicals involved with those things, and we're taking it out of the Earth where it's been for millions of years, and we're chemically changing it by combusting it and burning it and shooting it up in the air in the atmosphere. And we're doing this by the millions of tons per year. So of course, that's going to have an effect on the equilibrium of this planet. And what this planet does, and why the climate is changing, and why we have more storms and more intense storms, is this planet is trying to work back to that equilibrium. It's a cycle. Everything is a cycle. So as much as we want to sit here and put our heads in the sand and say, oh, we're not affecting anything, well, this is natural. Well, coal was formed by nature, so why is it bad for us to use it? Well, it was put by nature in a certain place, in a certain state, for a reason. And now we've disrupted that. So that means that disruption has to have an equal or opposite reaction, and that's what the climate is doing. It's reacting to what we've done to this material. So in addition to that air pollution that we're talking about, we have the greenhouse gases, we have the acid rains. We also have things that are just like physical spills, like when an oil line ruptures and we dump millions of barrels of oil onto a landscape, or when the Deepwater Horizon ruptured in 2000, I think it was 2010, we put like several 100 million gallons of oil into the Gulf of Mexico. It ran for like 86 days, I think. So this is another example. 1989, this is when I was in college. The Exxon Valdez ran aground in Alaska. And you can see here, this is where it ran aground. You can see the oil slick emanating from that. These were pristine, untouched waters out here. And you can see, this is where it ran aground right here. And you can see the movement of this oil spill over time down the coast. And what this did was it basically destroyed this ecosystem in this area really up until today. I mean, on the surface it looks okay today, but there's a lot less animal life in this area, and all you have to do is dig down into the sediment on the beaches and you will come to a layer of oil very quickly. The thick, tarry, crude oil, you'll come to that very quickly. So up until today, and this was in 1989, it takes probably hundreds of years for this stuff to reintegrate into nature once it's released in that form. So now we're going to talk about energy usage. And we've seen a couple of, I think the last chapter we had one on mineral usage. This is energy usage. And we can see on these charts, the green is consumption percentage, and the white is population percentage. So you see like China, their lines are kind of, they use more consumption, they consume more energy than we do, but they also have a lot more people than we do. They're close. Look at ours. Our population is small. I think our population is like 4 or 5% of the world population, but we use like 20% of the total energy in the United States. Our footprint, we looked at that mineral footprint in the last chapter. Well, this is the energy footprint. India is the opposite. They're the third largest user of resources, but look at their population. It's also huge. So per person, they use a lot less energy than us or China does because they just don't use that much per person, although in total they have so many people, they're still using a lot. And we are the three biggest users of energy in the world, and we use almost a vast majority of it is from oil and coal, is where we get our energy. So again, here's some charts that kind of tell you where our energy consumption is. This is based on the type of energy consumption. So industrial, like factories and stuff, is going to be 33%. Transportation, so all of our driving habits, is 28%. Our homes, residential, is 21%. Commercial, like just businesses, non-industrial businesses, is going to be 18%. And then over here, this is the kind of fuel that we're using. See, natural gas has jumped way up in the last couple of decades as compared to coal has dropped. Oil is still by far the biggest because of the transportation primarily. Nuclear is somewhat relevant here. And I will take this chance to kind of mention nuclear really quick. It's a very controversial type of energy source, and I'm kind of on the fence about it personally. Because nuclear allows us, of course, we have to mine the nuclear material, but you can get a tremendous amount of energy from a very small amount of nuclear material. So really the mining is not that big of a deal because its footprint is so small. We just don't have to have that much of it. It produces a tremendous amount of energy. The problem with nuclear is it's very dangerous if something goes wrong. If we do it right and we contain that nuclear material, and when it's spent, we properly contain the waste product, then that would be the best energy source that we have because a small amount goes so far. We could power this planet for thousands of years on nuclear alone. But the problem is I've alluded back to this several times, and y'all probably think I'm just terribly negative. But the problem is we're humans. And humans inevitably make mistakes and are careless and don't take care of things. So there's always going to be a mistake. And with nuclear, when a mistake is made, or if it's used to weaponize in some way, it can be catastrophic with just one mistake. You could wipe out a whole area with just one mistake. So it's kind of a high benefit, but it's also a high consequence type of endeavor. So it comes down to, do we trust humanity to be that responsible to use it? That's the question. And that's why I'm kind of on the fence about it. Right now, we see in Ukraine. Recently, I don't know, probably y'all don't watch the news as much as I do, but the Russians have been bombing around their largest nuclear facility in Ukraine. If they were to decide to go ahead and just bomb that and blow it up, it's going to create a tremendous area of nuclear fallout in that region. It's going to destroy an entire area, ecosystem, people, everything. It will be unlivable for years. So that's why even a nuclear power plant could be weaponized if somebody decided to say to bomb it, or a terrorist decided to hit it, something like that. So I just wanted to kind of throw that out there on nuclear because we don't talk much about it in this chapter, just on the surface. So here is the types of energy that these countries use, and I want you to look at these just in comparison. So here's the big three that I talked about. Fossil fuels, which is your oil and coal, 87%, 84, 92. That's just unacceptable because that is not going to be able to be continued into the future. It's not sustainable. You look at France, they still use a pretty big amount, but they also have a lot of nuclear in France. They trust their people more, I guess. And they have some of the renewable and hydro. But you look at countries like Sweden and Norway, so let's say that the war in Ukraine breaks out and becomes a world war, and we no longer can import gasoline or crude oil from Saudi Arabia. Sweden and Norway are going to be fine because they've transitioned away from those. They still use them some, as you can see here, but they have other sources that they use. They're going to be fine. Whereas these three right here, we're all going to be in really big trouble if something like that happens. So this is where politics really comes into this whole discussion about our energy resources. And that's a message that I think that the environmentalists have failed to get across to the general public. So everybody recently has been griping, and I'll just throw it out there, they griping about Biden because gas prices are so high. And as you've seen as we've been talking, it's not necessarily Biden's fault. I'm not taking one side or another on that. I'm just stating the facts here on what causes gas prices to go up. But nobody is stepping back and saying, you know what? If we'd have gone to renewable energy 20 years ago, we wouldn't have to worry about gas right now. We would be fine on our own. We wouldn't have to worry about importing gas any longer, because if we'd gone more to green energy when we could have, and that could have started 20 years ago, we wouldn't be dependent on other countries, and we wouldn't have to worry about this stuff. But for some reason, nobody wants to make that argument because it's not politically expedient for anybody. And to be blunt, the reason that more money has not been put into nuclear or hydro or renewable energy is because the fossil fuel industry has a lot of money, and they pretty much control our government. I'll be blunt about it. And I'm not talking about one side or the other. I'm talking about both sides. They have a lot of influence, and that has kept back the development of these other technologies in the United States. Because you can see right here, Sweden and Norway are able to do it. Now, they're smaller countries, I know, and they have less of a population, but they're also very intelligent, and they make adult decisions in these countries. So here are some examples of proven reserves of different elements. I'll let you look at that in your textbook. Here is just kind of a chart of the crude oil practices that I was mentioning and historical and political events. You can see how different political events, economic events, even scientific events can affect how we use and utilize oil. And it's very evident from some of these, like the recession in 2008, COVID most recently, that we can also just conserve it and not be as lax about driving everywhere. Having more public transportation. If we just cut back on our usage, that would also make prices go down. It's supply and demand as well. So here's what we call the peak oil theory. This guy named Hubbard developed this several years ago. And basically what he theorized was there's going to be a time, we're going to ramp up our oil production, and there's going to be a time where technology is going to slow enough that we're not going to be able to produce as much as we need. And then we're going to be on the downward slope of this curve. And that basically happened to the United States in 1970. That's why we started at that time importing oil from the Middle East, and we still do to this day. Now, at some point, that same curve is going to hit the Middle East. It already is. They're already producing less oil than they did for the last few decades. And they're having to move to different reserves because some of their larger ones, they're not out. They haven't run out yet by any means. However, they're producing less and less over time. And at some point, that's going to go down to a point where they can no longer supply what they need to supply. So that's basically what these charts are saying. And the chart on the right is just showing oil production in these individual countries and when that peak was supposed to have happened. And they're not right on time. I mean, they didn't predict exactly, but they did pretty good, actually. It came pretty close. And here we have this. This is just a kind of a blown-up version showing what the different lines mean, the reserves, the lower-end reserves, the higher-end reserves. And you have a plateau where you're going to be fine, and then you're going to start this downward decline. And on this downward decline over here, it's one of those moments you're like, oh, crap. You know, nobody wants to deal with this now. Nobody wants to talk about this transition right now because it's not politically convenient. We don't want to talk about prices going up. Nobody wants to address it because they'll be the bad guy. But once it starts, it's going to be too late, and you're going to have to find a solution where we could have been working on this the last 10 years and been prepared for a solution. So here we have another chart that has the growth in the world oil demand, not just in the United States. And this is showing current oil fields versus additional oil fields potential and then from our new fracking technology, what we'll be able to put out there. So at some point, this line's going to go up here, and all these other things are going to start to go away because we're going to hit the end of reserves, and we're going to have to find something else to do. And here's another chart. This is kind of projection. Remember, the tight oil reserves are basically fracking in these more dense layers. So traditionally, we've used very little of this, and we used all conventional oil. But going forward in the future, that tight oil is going to have to increase dramatically. And as we're going to see in just a minute, there are environmental issues with fracking. Definite environmental issues. And here we just have a chart of the different mineral types, or energy types, I'm sorry, and their usage over time. And you can see how some of these, nuclear, renewable, are growing, both growing. Coal has declined, natural gas has increased the last few years, and oil continues to increase. Although this textbook, again, was done in 2018. So you're going to see a decline on out here due to COVID. You're going to see oil and probably these others as well drop due to COVID and the Russian invasion of Ukraine. Let's click that slide. This is just a blurb in your textbook about vehicle efficiency. This is another way we can serve by our technology with vehicles, making vehicles more fuel efficient. That was a big push for years. Now we're almost transitioning. Everybody's going to electric vehicles now. So now we're going to get into this fracking a little bit. So the fracking is those tight oil reserves. You get down here to these very compact, dense layers. And basically what they do is they go down here, they drill their holes, and then in order to fill voids that can be where this oil and petroleum can be taken out of here from this rock, they have to break it up. So basically what they're doing is they're creating more pore spaces for that oil to occupy. And when it's occupied, then they can pump it out. It'll come out of the rock. If it's just in the rock directly, it's hard to squeeze it out of there. But if they make holes in the rock, i.e. bigger pore spaces, then that oil will fill in there and then they can pull it out. And eventually, over time, they'll pull it all out. Now, this is a slower process. It's very damaging to the environment because, again, remember what we're talking about here. We're talking about layers of rock deep underground. You're going down there, and at first they blasted them. They would send charges down there and actually physically blast it and crack the rock. So you can imagine that wasn't great for people who are living around there. Even though these were really deep, do you want somebody blowing up explosives 1,000 feet below your home? Probably not. Now what they've done is they're using high pressure liquid and chemicals they pump in there, and the force actually makes the rock split apart. Now you might think, well, that sounds better than a blast. Well, not exactly, because this water and chemical mixture, remember there's a lot of chemicals in here, it goes down there and it pops open these cracks in the rock, and they stay open because of the chemical composition. There's actually a lot of sand in there that keeps those cracks open, for that's good. But then they have to pump that water back out before they start mining the petroleum. So where does all that water go that has all these nasty chemicals in it? Well, they throw it in a holding pond somewhere and hope they don't have any problems with it. Sometimes they can treat it. Sometimes it sits in those ponds for years. So what could possibly go wrong with that? I mean, we've seen plenty that can go wrong. In addition, there's a tremendous amount of increase of earthquakes in these areas because you're changing the structure of the bedrock. It cannot take the pressure changes. Again, it was static. It was at an equilibrium, and then humans go down there and start messing with that equilibrium, and boom, you start having earthquakes. Some of them big enough to damage things. So that's the end of the slideshow here. Again, I hope you take something away from this. This is a very interesting chapter, very current and modern with regards to our politics and what we're discussing in this country. So let me know if you need anything, and we'll continue some of these types of discussions in the next couple chapters. So thanks.